Doctor, welcome back. Now, what about that? If we can measure the expansion, even measure the increase in the rate of the expansion, it seems to me we could task a computer with looking at these various bodies and work backwards and come up with something like a point of origin.
Well, it doesn't really quite work that way as far as we understand, because there isn't any such thing as the point of origin. It's not that we don't know where it was. It's just that the expansion of the universe is something that happens everywhere in exactly the same way. So it's true that here on Earth we see different galaxies moving away from us in all directions of the sky. But if you were on one of those other galaxies, you would also see all the galaxies moving away from you in all directions of the sky in exactly the same way. So the universe seems to us on large scales to be completely uniform. And when we say that the universe is expanding, we really just mean that the distance between every galaxy and every other galaxy is getting bigger. And that's not a statement about moving away from some point in space.
Right.
The statement about space itself just getting bigger and
Finally got it. Okay. And here's another one for you. If everything is expanding at an ever-increasing rate, then, unless I'm wrong, we measure the distant points of the galaxy with light, for example, from pulsars. Is that correct?
That's right.
Okay. Well, then what about light itself, which is moving, well, at the speed of light, right? And on outward. You know, that's, we see it 14.5 billion light years away or whatever. So, isn't this same force affecting light? And if it isn't light eventually going to get pushed over its own threshold?
Well, what's going to happen is that for any individual galaxy, it will move so far away that the light it emits will never, ever get to us, even though we wait this number of years. So we'll be able to see fewer and fewer galaxies in the universe as we wait longer and longer. Both because their stars will stop shining and because they get so far away that the light is never going to reach us.
Stephen in Los Angeles, you're on with Dr. Carroll.
Yes, good morning, Bill.
Good morning.
I have a thought experiment. Suppose there is a particle immediately before the Big Bang. There is a single point particle. Is it possible that in a collider, while looking for the Higgs boson, whatever, we instead found this first particle, this God particle, and sometimes they call it Higgs, the God particle that I'm talking about, the particle that actually was there before anything else. If we were to observe that in the collider, would there be any possibility that the whole universe would be annihilated to the pre-Big Bang state?
Well, there's two things. One is that I'm not quite sure what that would mean. What it would mean for there to be a single particle before the Big Bang. We think that there were many particles as soon as the Big Bang happened. And it's interesting that there are only a finite number of types of particles. You know, at that time, there was no rule. We didn't know anything about particles. That there weren't an infinite number of possible types of particles. But we think that the number of types is very small, but there's just many examples of them. And it's a big universe, and there are many examples of each different kind of particle. But the reason why we're pretty sure that nothing so dramatic will happen when you start colliding particles together in CERN or other particle accelerators is because, like I said before, this has already happened in the history of the universe. All the time, out in space, very high energy particles smack into each other with much higher energies than we're going to ever make. That we're going to make anyway at CERN. Maybe someday we'll get to those high energies. We're not anywhere near there yet. So the things that we're doing in particle accelerators have already been done in outer space. It's not a new phenomenon for the history of the universe. The thing is that we're going to be able to observe it with exquisite care in a way that we haven't been able to do before.
Okay. And this has all happened without universally catastrophic results.
That's right.
Jim in Bellevue, Washington, you're on with Dr. Sean Carroll.
Not yet.
Yes, I have a couple of hypothetical question. I'm wondering, let's say for the sake of argument, there was a black hole that was oriented in such a way that the jet from the black hole were to stream down onto the solar system. What effect that would have on us here on Earth? And the second question I have is, if a large brown dwarf-sized body were to move very fast so that it wouldn't actually collide with the Earth, but was to pass, let's say, within the orbit of the moon, what kind of tidal effect that would have on the ocean?
So these are good questions. I think that they're very different answers. So the one for the black hole, that is beaming stuff, is very small. In either case, it's very good news. The universe is a very sparsely populated place. There's bad news. Travel from star to star. They're light years away from each other. But it's very good news if you have some concern about running into some other celestial object. The chance that the solar system will be saved by another black hole or a brown dwarf or anything like that is very, very, very small. Everything we haven't talked about how the galaxy is arranged. But it could happen in a chance. So you're certainly allowed to think about what would it look like if a brown dwarf came into the solar system. Then that would depend a lot on exactly how heavy it was. Brown dwarfs are generally heavier than the planet Jupiter, but smaller than the Sun. So Jupiter already exists in the solar system, and it has a tiny but measurable effect on the motion of the Earth and the Moon. If it came very close to the Earth, that would have a huge effect. It would wipe out life here on Earth. It would, fill the oceans from side to side and tremendous earthquakes and all of that. But the chances of a black hole being anywhere close enough to Earth to have some substantial effect are even smaller than that. We think that the galaxy is full of brown dwarfs, but there are very few black holes compared to the number of stars. It's much more worrisome to worry about if another star being way close. So I wouldn't worry about that more than black holes. I wouldn't worry about either one of them very much at all. Sure, why not? There's 100 billion stars in the galaxy. They're all moving around. Occasionally they will collide, or occasionally they will pass by each other at very close range. But the point is that even though there are so many stars, the galaxy is a very, very big place. So these collisions happen very, very infrequently. It's not something to worry about in terms of the list of interesting things you should worry about. It's low on that list. But it's certainly something to contemplate.
But probably would rather not.
I would not hope that that would happen.
Marlon in Science Center.
Greetings, gentlemen. It's a pleasure to speak with you. I have two quick questions. My first question is regarding the concept of infinity. I don't understand the idea of saying how something without measure can be bigger and then bigger again, because it suggests bigger means that it was one thing and now that it's a